everyone, and thanks for coming. I must say it's a great pleasure to be here again on the stage, and it's a pleasure to meet you in person. My name is Tomasz Stradomski. I'm Principal Data Engineer at Ocado Technology. As Paweł mentioned, I was involved in building and reshaping our data platform almost from the very beginning. Today I would like to tell you how our data platform and data processing model looks like and how it evolves over time. But before doing that, let just me quickly tell you what we do in Ocado. So basically Ocado is the world's largest online-only supermarket. We operate in UK. For the last several years we significantly grown. At the moment we have 11 development centers in 7 countries, and we hire more or less 2,500 of people in IT. The heart of Ocado are fully automated warehouses, which we call CFC, Customer Fulfillment Center. So you can imagine that on the grid of the size of several football fields, you have hundreds of bots like that one on this picture that are moving, carrying item and doing different kind of operations just to fulfill orders for our customers. But Ocado is not only CFC. Actually, we created software for end-to-end customer experience, starting from doing shopping online till home delivery. So on one hand, Ocado is online supermarket, but on the other hand, we sell our solution as a service. This opportunity is called OSP, Ocado Smart Platform, and we have a pleasure to work with multiple partners all over the world. So we built our CFCs, for example, in Canada, in US, Australia, Japan, and also several in Europe. Actually, there is upcoming project also in Poland. So migration to the cloud gave us quite unique opportunity to rethink and redesign our systems, and that also includes data architecture. So when designing the data architecture, we have several principles, but the most important one is that we would like to have the data processing so easy that everyone in the organization can do it. In Ocado, we believe that to build truly data-driven company, we need to enable not only specialized teams like data scientists, data analysts, to be able to process the data, but everyone, every single team member, software engineer, manager, product manager should be able to access the data and derive some information from the data we collect. Actually, data is extremely important to us. That's because we live from doing optimizations and automation. So let's take a look how we collect the data. So we don't have any traditional ETL processes. We don't extract the data from operational databases. We use event sourcing approach. Actually, Ocado Smart Platform works in 2 clouds. We have our business application in Amazon Cloud, and those applications are responsible for sending the data in form of events. So when there are some business operations being done, for example, customer makes a new order, there is a payment taken from customer account, or the order has been delivered to the delivery address. Application send the event. All those events are sent to a stream in Amazon Cloud, and this is Kinesis. From there, we created application called Event Processor. After this talk, you will have a chance to hear more about Event Processor. But in a nutshell, Event Processor is responsible for downloading the data from Kinesis and streaming it to BigQuery. BigQuery is data warehouse solution in Google Cloud with SQL access. It's very scalable database that follows asynchronous massive parallel processing paradigm. So this is how we load the data. But if it comes to data transformation, this is how we do things. So basically we have three areas. So all those events that has been streamed and sent by business application are streamed to BigQuery tables. And this is the private area for the so-called data producer. Data producer is a team that produces this particular piece of information, those tables. This is private area because there may be a lot of changes there. New versions, some changes in schema, some updates. So from our experience, if you rely all your business logic on this kind of private, frequently changing area, it may fail at some point because of backward incompatible changes. So we introduce something that we call data objects. This is internal API. And the data producers, so development teams, are responsible for creation those data objects. Data objects are in most cases views, but also physical tables that are being refreshed several times a day depending on the concrete need. What is important, data object contains the data from one area only, one business area. For example, from order management or delivery systems. From there, we created third layer, which we called derive objects. It's a little bit similar to data objects. Also, data producers maintains that and creates, but it may contain the data from different areas. So it's a blend of data. For example, order management joined with payments data, with delivery systems data. We call it also sometimes external API. That's because this is the data that we share with our partners via Google Cloud Storage. As mentioned before, data producers, so development teams, are responsible for creation of the data and derived objects. And in 90% of cases, those are SQL objects, views or tables built by SQL queries. Let's take a look on some statistics. At the moment, in total, we have more than 14,000 of objects. Because we deploy our things to different environments for different partners, we have more or less 870 unique data objects and more than 100 unique derived objects. So from May 2016, we built on average 14 unique objects per month, but this number is significantly growing. And all those things are done in SQL by development teams. So SQL has pros and cons, of course. Some teams likes it, some not. We have a lot of views, a lot of quite complex workflows, which over time grow and process more and more data. And at some point, it may be problematic, especially for teams that are not specialized in this area. So we don't have hundreds of data engineers. This is done by software engineers. So taking that into consideration, we started a project that we call JDP, Java Data Processing. So the idea is to enable data producers to be able to process the data in a little bit more familiar technology, for example in Java. And one of the consequences of that is that the data is also processed in real time. So we use 4 technologies from Google Cloud in this project. Those are cloud functions that allows Lambda-like architectures. So basically, cloud functions are triggered by events. So they listen on some queues or topics and execute exactly once for each message, for each event. PubSub, this is the messaging system in Google Cloud that we can use for event-driven and streaming analytics. Data store, this is something that we use for cache. It's highly scalable NoSQL database. And last thing that we use partially is Dataflow. This is managed service for executing Apache Beam operations in Google Cloud. It's similar to Spark. So if you are familiar with Spark, Dataflow is a little bit similar. We use it for operations like initial data migration or backfills. So the idea is, this is something that you already saw a minute ago, but the idea is to enable not only loading the data into BigQuery, but also stream processing. So event processor till now has been loading the data only to BigQuery, but there is a special second path which allows streaming the data directly to pub subtopics. So from there we can use those streams for additional transformations and analytics. So let's introduce two types of events. First type is called dimension, and second is called main or fact event. This is the naming convention, a little bit similar to traditional data warehousing. So you may have heard something about that, and the concept is similar. So basically, dimension events carry some additional attributes that can be added to your main data, to your fact data. In SQL, you would say that this is the table that you join into your main table. So the idea is that you have stream of dimension events. For each event, there is one execution of cloud function. So you can express your business transformation in Java, do some renamings, transformations, mapping of fields, whatever is necessary, and store the results somewhere. And here it's useful to store the data in data store, which is, as I mentioned before, scalable, NoSQL database. So we use it as a cache. So this data is available for further processing in data store. Second type of event is main event. So this is your fact data, the most important information. So again, there is a stream of main events, one execution of cloud function per event, and what you can do is transformation, plus you can enrich the data with your dimension attributes. So in this case, what you need to do is look up to your cache by index, take those information derived columns and add to your fact data. And again, now you can send it to data store to be available for other functions, stream it to another pub subtopic, or stream to BigQuery. So basically, once it's streamed into BigQuery, it's available for SQL operations, for data analytics, for machine learning, for whatever is necessary. There is one important factor here, because we operate in cloud, and the order of delivering of messages is not guaranteed. So it may happen that your main event arrives to your function, to PubSub, before dimension. That basically means that dimension is not available in this specific point in time. So we implemented a kind of retries or resend mechanisms. So basically in data store there is a special area, let's call it to be retried table, that is dedicated for storing events that hasn't been fully processed till now. And there's another schedule function that just grabs all those events and stream them once again to your PubSub as main events, just to repeat the operation and try to do the join once again over time. So this is the idea how it works. You can implement quite a lot of features there. You can implement aggregations, store your partially calculated results in cache to retrieve them later, and things like that. So let's take a look on almost real life example. So let's say that we have 3 streams or events. First stream contains information about our orders, some details of the orders, the items that has been ordered by a customer, about substitutions, promotions, whatever is necessary in context of order. Second type are informations about delivery. So let's say this is planned delivery. So information about addresses and expected delivery times, for example. And let's say that we have some additional delivery details in dimensions that carry some information about actual deliveries. So this is theoretical, this is the plan, and let's assume that a delivery agent has a device with the application, and after doing delivery just confirms that delivery has happened in this particular point in time. So we have detailed information about actual delivery, and we would like to join this data together, transform it, and make it available for reporting. So first step, we have 3 PubSub topics. Delivery details are stored in the first one, and there is the function that is executed, and it does some transformation on this data, and the results are stored in cache. So those are transform delivery details events. When we have delivery event main, there is another function that transforms this data, reads the data from cache, and streams it, for example, to BigQuery, and from there so-called delivery data object is available for analytic operations. This is detailed information about when has happened this particular operation and all other details. But it can be also streamed into another data store table. And we have third event, order event main. Actually, this is stream of events. We have a function that runs some transformation, sends it to another PubSub topic. Another function grabs those transformed orders and reaches them from cache with some delivery information. So let's call it order delivery derive object. This is derived because it combines the data from 2 systems, and again streams it to BigQuery. So this data is available for both batch processing using SQL, but also because of this chain of executions for doing real-time operations and real-time analytic. And from our perspective, there is several benefits of such an approach, especially for data producers. For sure, easier testing. So basically, you can test pieces of your Java code. You can emulate some cloud resources like PubSub topics, data store. So you can build emulated environment on local machine to be able to test it end to end. You can also release to the cloud and run your whole pipeline in the cloud for a kind of end-to-end test. Comparing into testing of SQL, it's completely different. In SQL, you need to generate some test data, run your query, assert on some expected result. It's more complex. We have less views. So, as mentioned before, views are great, but if you have a view build on the top another view and another, at some point it may be a little bit complex. In JDP we follow a rule in which the data is processed once and the result is stored. You can enable real-time monitoring and alerting, and it can be both technical alerting but also business alerting. So in previous example we can imagine that we have expected delivery at 4 p.m. but actually the delivery has happened 2 hours later. So for example, in this case you can set up an alert, a kind of business alert, to inform, for example, promotion team that this particular customer may be not satisfied because of delivery has been delayed, to run some actions. We also measure the data quality and we define SLA for the data that we build and that we expose to our partners. So this is another thing that you can do in real time. There is a massive cost reduction because in SQL you need to repeat the same operations many times. So for example, we have a lot of queries, a lot of tables that we refresh every 15 minutes. So in this case, the same query is executed 96 times a day, and in BigQuery we are charged by the volume of the data that is being scanned by SQL operations. So basically we pay 96 times for the query. Here you pay only once. It's also more flexible approach. So again, we can imagine quite a lot of different use cases. For example, you can stream the data to memcache to be available for machine learning or something like this. So those are just examples: BigQuery, data store, PubSub things, but it can be extended by many others. So this is more or less all I wanted to tell you, and now I'm happy to answer your questions.
I'll just pass the mic so that it gets recorded.
I have one question about the data store, because am I understanding it correct? There is a data structure like a table, yes, and in this table we just copy a row from another database and paste it here. And I think that the data store table is a working table, and I have a question. What is the difference between data store and, for example, list of objects?
So first of all, data store allows you to process massive amount of data. We needed huge cache. So basically that allows you to cache terabytes of data in an easy way. And also we define something that we call time of life of object. So basically there is retention. Some data you need for 1 day to be able to join with different data and stream to BigQuery. So yes, this is a kind of massive cache. Yes, you are right, this is a kind of database, but it's no SQL, so you cannot query it with SQL. So it may be not that useful for data analytics team or machine learning if you would like to take a look on your data, and it doesn't scale that much. In BigQuery we store petabytes of data. In data store only terabytes, and yeah, so this is the main difference. For us this is the huge cache.
Okay, so but why not why not a list of objects with with data from that we need? Because of size of this data?
Yes, I would say.
Okay, thanks.
This is because of the performance. So actually we've been investigating also different things like Bigtable to be able to have even bigger cache and not to implement all those retention related things. But data store is fully managed on GCP. By the way, I should inform you at the beginning, but this is the product that is currently in beta phase in Ocado. So this is still in progress, it's still new, it's still a lot of things that we need to do here.
Okay, thanks for your answer.
Thank you.
Hey, Tomek, I wanted to ask you if there is any need, like what are delivery guarantees in this approach? Like I would say that it's at least one, because there was like a retry mechanism that you mentioned, but do you need to handle, for example, duplicates in this case? How do you handle that? And do you have any like late objects, I would say, that are stacked in some queue and will be delivered after, I don't know, few hours?
Yes, of course. So first of all, there is that event processor part that streams the data from Kinesis to BigQuery and PubSub, and the first place when delay may happen is here, or even in source applications. So yes, we have those delays. We just process the data when it arrives. So this is the first thing. Second thing, we handle duplicates by doing lookup to data store. So basically, Cloud Function, when there is a new event, Cloud Function does the lookup operation to data store to retrieve the current state of the object, and is able to deduplicate the data in normal Java way. So those are normal Java objects when they are loaded into Cloud Function. So we use equals and hashcode for looking for duplicates.
So at the end, it's exactly one semantics.
At the end is exactly once, unless there is so-called backfill. So you can imagine there is something wrong in your data and you need to process a day or a month of the data. So we run the backfill operation. So this is the point in time when duplicates may arrive, but we also cleaned all data. But at some point in time, you may see some duplicates. In general, in SQL, in BigQuery SQL, we advise to run the duplication.
Okay, thank you.
Sure.